Hello, good afternoon. Hello, good afternoon.
Good afternoon, sir.
Good afternoon.
Yeah. Can you all see me? Can you
Yes,
all?
sir.
Yeah. Can you all
Yes.
hear? Can you all hear?
Yes, sir. Yes, sir.
Uh, right. We'll start with our continue with our lectures on design and analysis of experiments. Up to last week, we have discussed about the basic principles of design, and thereafter we said about little on the border effects, basically, right? Today we will see some of the basic designs, and also one modern father of statistician called as Fisher from UK. He mentioned that when you want to analyze the data collection is more important before you do the analysis. The proper way of conducting the experiment is more important. Otherwise, if you conduct misled kind of experiment, and if you bring the data, that is something a statistician can look into the data and say why this particular experiment went wrong, where this particular experiment went wrong with data collection and planning the experiments, right? So therefore, everybody, uh, everybody, when you come to final year research, all of you will be doing your own research, own experiment. So most of you will fall into planning your experimental design, planning your experiments, right? So before we go to the real practice of experiment, you have to plan it, all right? So that plan has to be approved, and that plan has to be accepted by everybody. Then you can continue with experiments, right? What is this experimental design? What is this design, basically? An experimental design is a plan for the assignment of treatments to the plots in the experiment. Suppose, for example, let's say we have I have 4 treatment, right? I have 4 treatment. I will say I have 4 treatment. Let's say T1 to T4. That means T1, T2, T3, T4. 4 treatments are there. Now let's say I have 4 plots, right? 4 experimental unit. So this is first experimental unit. This is second experimental unit. This is third experimental unit. This is the fourth experimental unit. So now, which treatment going to come into first experimental unit? Which treatment comes to second experimental unit? Which is come to the third experimental unit, and which treatment comes to fourth experiment? So this is where we call it as randomization. When you randomize, suppose let's say the outcome of randomization, T2 is coming here, T4 is coming there, T1 is coming there, and T3 is coming there. So this is actually a process of randomization, isn't it? Isn't it? This is a process of randomization. Why? Because if you look at this, for example, this is T1. We are allocating T2 to second experimental unit. We are allocating T3 to third experimental unit, and we are allocating T4 to the fourth experimental unit. can you tell me where you can see the real randomization occur? Whether it is in A block, we will talk about that. Whether it is in A situation or B situation, where the randomization is really happen. Yeah, whether it is in A or in B, where the randomization occur. A. Yes, in A. Why? Because if you look at B, we have all 4 treatment starting from T1 up to T4. Simply we have allocated on a sequential basis to all the experimental unit one after the other. So this is not a good way to do the randomization. This is a good way to do the randomization. So you see, after doing all these randomization, replication, and so on, then you will have a final plan. So this final plan is the one which is called as experimental design. So this final plan, right? So once you give this final plan to everyone, they will simply accept the final plan. If they accept it, that means you have chosen the correct design. Okay? Right. Now we will continue. So design differ primarily in the way the plots are grouped before the treatments are applied. So design initially gives the information about how the grouping is done before the treatment is applied. How much, for example, how much restrictions is imposed on random assignment of treatments to the plant. So this is what we have already said, how we are going to do the randomization, which way that we are going to do the randomization. We'll talk about that later, one design by one. To design, this randomization process differs, right? Right. Let's take an example here, right? This is one experimental unit. This is another experimental unit. I mean, all are different experimental units. So you see, this is one experimental unit. This is another experimental unit, square shape. Huh? This is another experimental unit, and so on. So here A, B, D, A, C, D, B, C, and so on, right? This is one way of doing randomization. Look at these two. Look at these two. Can we accept? I mean, this is one way of doing. This is another way of doing. Can somebody tell me which one is correct? Which one is wrong? Or is this both are wrong? Or both are correct? And somebody tell me what is the situation? Randomization. We are talking about randomization. You see, how many treatments are there altogether? So these letters are each of these treatments. How many treatments are there?
12.
No. How many treatments
16.
are there? My question is, how many treatments are there?
3, 4, 4.
Huh?
4.
4 treatment, yes, 4 treatment, not 12, not 16, not 3. Treatments are the names of the treatments which has been assigned to each of these plot or experimental unit. So here A, B, D, A. But it doesn't matter. Here we have allocated these treatments. Fine. So we have A, B, D. From the first row, that is what we found it. In the second row, we have C, D is which we have already found, B and C. Then in the third set, we have B, A, D, C. Right. Right. Can somebody, so everybody said 4 treatments are there. Can somebody tell me which is, by looking at these two, which is most appropriate, whether this is appropriate or this is appropriate, whether 1 or 2.
2.
2. Why?
2.
Huh? Somebody said this is appropriate. You can put the answer in chat. I will check how many says 1, how many says 2. We could have done a small quiz. I forgot to have it. So yeah, how many says 1, how many says 2? I will read. Yeah. So it's look like most of you have said 2. Can somebody explain why 2 is correct? Why 2 is appropriate in this situation than 1? Why? We can't simply throw 1 also. 1 is also correct, but 2 is more appropriate. Can somebody explain why? Somebody said I didn't hear. In one sample, a treatment not applied. All 4 treatment are used. Exactly. So yeah, 4 treatments. Now everybody start chatting. So you all are famous in chatting, so that everybody chats. Don't forget this. All these chats will be recorded. Good. Okay, fine. So somebody said 2 is correct, 1 is incorrect. Why? Why 1 is incorrect? If you look at, let's say, this is one set. So this is the first experimental unit. This is the second experimental unit, third, fourth. 4 experimental units are there. If you look at the first, this is called as block, right? The first one. Still chats are coming. Let's check. One second. Each experiment. Yeah, so people have expressed their answers in different way. Can you mute it, please? I'm hearing please switch, mute it. All right. You see here, as I said earlier, we have 4 treatments. Look at in this case, if you look at this particular block, what is the treatment missing in this particular block? C is missing, isn't it? In this block, what is missing? A is missing. Now you don't put it in chat. Just what is missing here? Anything missing there? A is there, B is there, C is there, D is there. So nothing is missing. So everything is there. But look at these 2 blocks. This is first one, this is second one. If you look at those 2, those are blocked. Those in those 2 blocks, we are missing out some of the treatments, right? So how do you call that? I have already said, if some treatments are not appearing in one block, there's a name for that. Anyone? incomplete, isn't it? Incomplete. So incomplete. Right. The other thing is, I will just erase it. Now, in this in the first example, how many times A appearing for the whole treatment, whole experiment? How many times A appearing?
3.
3 times. What about B?
3.
3
Huh?
times.
Huh?
3.
3.
3. C?
3 times.
D?
3.
3 times.
D? 3
3
times.
times.
Okay, right. A appearing 3 times, B appearing 3 times, C appearing 3 times, and D appearing 3 times. Interesting. Now look at this example. How many times A appearing?
3 times.
B,
3 times.
C.
3 times.
What about D?
D also 3 times.
Right. Then why you all say 2 is correct? Because if you look at the replicate, number of replicate, A appears 3 times, B appears 3 times, C appears 3 times, D appears 3 times. In the second situation, same. All are appearing 3 times, which is called as replicate. Right? So is there any difference in replicate between these two setup? You can apply either 1 or 2 in the field. You can't apply both. You can apply only 1 or 2. In terms of replicate, can you remember we talked about the principle of experimental design? One of the principle is replicate, number of replicates, so which is equal in both cases. Right. Now, if this is equal, so we can apply the design 1 or design 2. Both designs are same. Then how we can justify that? 2 is better than 1. Anyone? Why 2 is better than 1? Because replicate is same. Anyone? Anyone? Because I couldn't hear properly. Maybe something wrong with the voices. Yeah. Anyone? What is the problem? I'll read the name. Smartly, you all have put the AG number. AG 996. What is the reason? What is the reason? What is the reason? What is the reason? AG 996. Are you wrong? AG 996. I can see. Who is that? 996. What is the answer? Yeah. What is the answer? Because we said that the replicates are same. I couldn't hear. Replicates are same. But still people are saying 2 is much more appropriate than 1. If you look at one block, you see all the treatments A, B, C, D. If you look at the second block, again A, B, C, D. If you look at the third block, again A, B, C, and D. All treatments are appearing in each block. All treatments are appearing in each block. But here, what is the problem? Here you see C is missing, here A is missing, In addition to that, here, what is the problem? In once, I mean, right here, everything is okay. In addition to that, C is appearing twice, A is appearing twice, and so on. So among these two setup, the most appropriate design that we can say is the second one, right? So somebody has already said in one plot, actually not one plot, it is one block, right? Okay, she is having some problem. She or he is having some problem with the mic, right? So yes, that is actually this is one block. This is called as one block, right? So this is one single block. In one block, all the treatments are appearing in case number 2. So you see, this 2 is more appropriate than others. So that is how these are planning. These you cannot do it directly in the field. These are planning. So after planning, then only we can get into the ground. Why do we need a design? Why do we need a design? What is the need of the design? To provide an estimate of the experimental error. We talked about experimental error earlier. So to provide the estimate of the experimental error, to increase the precision, blocking, and so on. We will talk about that once we come to the blocking. To provide information needed to perform tests of significance and conduct interval estimates. So basically these we will, when we talk about designs, we will be discussing this, right? So how the precision increase during blocking. We'll talk about this blocking later in detail. And also it provides information needed to perform the test of significant test. What do you mean by significant test? And also to construct the estimates, interval estimates. We will be doing all these, right? But you have heard about these terms before in your first course. Significance, how to complete the interval, confidence interval, right? How we calculate the confidence interval, right? Estimate, plus or minus. Can somebody remember? Standard. Anyone? Standard error of estimate. So this is how we put up the confidence interval, right? So this is constructing interval mean it is talking about the confidence interval. So whether it is 90% or whether it is 95% confidence interval, that we can decide, right? Right. The other one is to facilitate the application of treatments. Some of the treatments are difficult to apply. We need larger plot, smaller plot, right? We'll be discussing different plot size later on. So that is plot size, when the plot size differs. In an early example, what do you think about the plot size in this example? So this is a plot, right? Yeah, this is a plot. This is a plot. This is a plot. So here all the plot sizes are same, right? Sometimes in some other type of design, the plot size may be vary. All right. You see, this is one plot. I will use a different color pen, right? I'll use a different color. For example, so you see we have 3 plots, big plots. Now within plots you see right. In blue color, how many plots are there? This is 1, this is 2, 3, 4, 5, and so on. So altogether 12 plots are there in blue color. In red color, how many plots are there? 3 plots. What are those 3 plots? This is 1 plot, this is 2nd plot, and this is 3rd plot. So likewise, so this the plot size may be different. So that is why we said maybe for certain cultural practices, right? The plot size differ. For example, this is 1 plot. This is 2nd plot. 2 plots are there in big size. In small size, we have 1, 2, 3, 4, 5. So on the other side also 5. Altogether, we have 10 plots. 10 plots of small size and 2 plots of large size. You see, different plot size. So if the plot size differ, then the design also differ, right? So that is sometimes why the plot size is. You need to have different plot size. Anyone? For example, my treatment is one treatment is using tractor, plowing experiment. One is using tractor, right? The other one is manual, for example, right? So here this green color I'm using for tractor, and the other one is for manual. Why we want to have large plot for tractor? I mean for this character ploughing, because tractor cannot turn on a small plot, isn't it? So we need a more or less a larger plot. Right. The second aspect is variety. I have 5 variety. Variety 1, variety 2, variety 3, up to variety 5. So I can put different variety here. V2, V1, V3, V5, and V4. So likewise, I can fill the variety there. So that's why the variety is coming into the small plot and the ploughing exercise coming into the larger plot size. So that is the need of the plots, right? Need of the cultural operations. Any questions? If you have any questions, you can put it into the chat, right? I can read the chat. Right. When you plan a design, what are the factors basically that we should consider? When you plan a design, what are the factors that we should consider? Physical and topographical factors, especially if you come to the land. If you are going to do experiments on the land or in the field, then the physical and topographical features. What do you mean by topographical features? You heard about this topographical. Physical environment. Physical environment means if you take a land, physical environment, whether it has soil, whether it has boulders, whether it has small pebbles, etc., etc. So what direction these physical characters are changing, and so on. What is topography? What is topography? Anyone? What is topography? If you take elevation, for example, right? If you take the land here, cannot be compared with the rest of the places. Let's say A, this we have discussed last time, B and C. If you take the land, three places, the conditions in these three places are not similar. So we will have to consider the topography always when you plan your design, right? The other feature is soil variability. This we are talking largely. The soil is vary from place to place, isn't it? So if you take maybe people who are majoring soil science, I'm taking two places, A and B. The distance is 20 meter, just 20 meter. So this is one place, this is another place. How many of you argue with me that the condition in A and B are almost same? Anyone in specializing soil? I'll have to take a list. Huh? I have all the information in the bag. Anyone doing soil, or even others can answer? Can you tell the condition when you take soil condition? Maybe nutrient in A and B, or the level of microbes in A and B, or maybe the moisture level in A and B. So when you consider these two sites, can somebody tell me whether there would be a difference between these two sites, or no difference between these two sites? Can you all rename your name? Are difficult to get your age numbers. Everybody is with age number. Yeah. No names are there. Hmm? Yeah. Yeah. Somebody said different. Yeah. Good. Usually, these are different. Actually, there will be a difference between these two sites in terms of any physical or chemical or biological characters of soil, right? Any characters. So nutrient level or microbe level, anything. So they are different. Right. So that is about the soil variability. So we'll have to consider the soil variability. Then number and nature of the treatment. So what are the number? How many numbers of the treatment? I have seen so many problem in getting this nature of the treatment. For example, I'm going to test the department recommendation is urea, let's say as a basal dressing. I don't know urea. What is the basal dressing for paddy? Anyone? How many kilograms per hectare? Anyone? What is the basal dressing for paddy? Urea. Basal dressing, usually we are applying urea only, right? I mean urea or ammonium, right? Ammonium sulfate, doesn't matter whatever it is. Let's say urea. Just an example, I am saying 100 kilogram per hectare. I don't know actual value. I'm just taking one example. 100 kilogram per hectare. Now Your objective of study is you want to reduce the urea percentage and see how whether the yield is reduced. So when you talk about yield reduction, you can reduce 1%. You can reduce, if you reduce 1%, what is the amount that you are applying now? That is one treatment. I will. So let's say urea, we are applying as a basal dressing 100 kilogram per hectare. So that is the application. Now I am going to reduce my objective is, right? My objective is reducing urea as basal dressing. This is my final year research. So how I'm going to reduce the urea? Let's say I'm going to reduce by 1 kilogram per hectare. So that means first treatment is you are applying 99 kilogram per hectare. This is treatment 1. 99 kilogram, or you are applying only 99% of the total urea that is practiced. So this is treatment 1 as an example. Second one is you are applying 98%. So 98 kilogram per hectare. So this is 98%. I'm putting everything in detail, right? So likewise, we can reduce gradually the urea percentage, right? Suppose in the same experiment, if I decide my treatment as, let's say, T1, reducing by 50%, reducing by 50%, or reducing by 25%. Do you think it is a good idea to incorporate this kind of study directly? Reducing 50% of basal area from the recommended dose. Do you think it is a good idea? If it is good, tell me why. If it is bad, tell me why. You can write it on the chat. We want to reduce the basal area and see whether the yield is affected, right? So we are going to reduce the basal area gradually. So can you tell me whether reduction in this way is better or reduction in earlier way is better? So in earlier way, reduction is something like this: 99, 98, then next one is 95, and so. Then this reduction is very vast. Yeah, somebody said bad, there will be a great negative effect on plant. Somebody said the earlier way is better. It is difficult to get an idea how the urea affecting the yield when reducing by 25%. Bad, sudden more reduction reduces the growth and yield. Not good, reduce by, yeah. So all you have in the same idea, right? All you have the same idea, that is fine. But the explanation is a little bit different, but it is fine, right? What is the explanation that we can give? Now, when you say recommended fertilizer, when you say recommend, who is recommending? Recommendation given by the Department of Agriculture, right? Recommendation given by the Department of Agriculture. So they have done a lot of research. Based on that, they have given the recommendation as 100 kilogram as the basal area per hectare. Now, if you reduce suddenly 25%, it is not a good idea, because definitely there may be a huge yield reduction, huge impact compared to if you are reducing only by 1%, isn't it? So look at this 1% reduction and 25% reduction. Then second step is 2% reduction. That is how we'll have to do it gradually. Gradually you reduce the percentage. So here we are reducing 25%. Next one is 50% reduction. So this is not a good criteria in terms of reduction, right? Right. So we will. So that is why we said the experimental, number of treatments is also important, and nature of the treatment, that is also important. This is what we have already discussed. Nature of the treatments. So we can't choose the level that we want. We'll have to adhere to some kind of criteria. Then experimental materials. We talked about this earlier, controlling the unexplained variability, crop, animal, pathogen, etc. Right? So it's depend on the experimental material also. What material that we are going to use, that we'll have to consider it well in advance. Did I mention last time when you do this PAPO experiment, PAPO germination, we can't collect the seeds from simply from the market. Why? There is a huge variability already among the seeds, so that we cannot get the seeds from the market. So likewise, that is one example for the experimental material. Then duration of the experiment. So how long that you are going to do the experiment, what machinery is to be used if you are doing agricultural experiments, size of the difference to be detected. So this is one of the important key feature, size to be detected, right? So based on the size to be detected, if the size to be detected very small, right? The size to be detected may be slightly larger. Size to be detected is maybe very larger. Size to be detected may be very large. So you see, if you want to detect the difference in terms of size, there is a small and large. So here we need less effort. Here we need little more effort. Here further high effort. Here high effort. So that is how we need to have the experimental stages. So different efforts have to be there when you do the experiment. Significance level. So significance level basically that is depend on alpha, right? We can consider alpha as 0.05. That is one alpha, right? 0.05. What are the other alpha values that we can use? 0.1 and the low value 0.01. Can you remember we discussed about these alpha values? Right? Whatever the level that we'll have to justify. Right? Experimental resources, what sort of resources that we have with the land, the size of the land, other type of resources, amount of financial support, etc. All these are, financial coming separately. All these are important when you plan a proper experimental status. So these are the factors that we can consider. Right. What are the rules? Some of the cardinal rule. Right. These are some. Choose the simplest experimental design that will give the required precision within the limit of the available resources. So don't do some complicated things. So if you don't know how to write essay in English, all right, if you have problem writing essay in English, how people advise, don't write a big sentence. You write small sentence. If you write small sentence, then you can simply get rid of that problem, isn't it? If you try to write sentence with 20 words or 30 words at once, then you will be in trouble, right? So similar to that, here choose the very simple experimental design, whatever the design, right? But on the other hand, this design should give very high precision. It should give very high precision, all right? So that is important, using the available resources. Right, what are the assumptions? Can you remember in first course, we took some assumptions when we did pool t-test, pair t-test. Can you all remember? Pool t-test, pair t-test, then we did regression. Right, so here also we have certain assumptions to be taken. The first one is normality assumptions. Normality assumptions. That means the data is normally distributed. The data is normally distributed. Data is normally distributed, right? So these are some of the ways that to see whether this is normally distributed. So you can plot and see that the data is normally distributed. So that is first thing is that you can plot. Oh, nowadays some test is available. It's called as Kolmogorov test. Kolmogorov test. So which gives whether data is normally distributed or whether the data is not normally distributed. Right. Second thing that should be considered as the assumption, the variance is constant. Can you remember when we did the pool t-test? We have written something like this. How many of you can remember? We can test for this. What do you think? How do you call the test of this? Testing for this, anyone? Can put it on the chat. Test of that. So in certain cases, in almost all the cases, we should test it. Yeah. So can you remember homogeneity test? Homogeneity of variance. We test for homogeneity of variance, right? So that also we can test using the plots, drawing the plots as we did earlier, or we can test using Leven's test, homogeneity of variance. The last one, the error variance. Error variance. So error variance is distributed normally with a mean of 0 and with the error variance. So error is distributed normally with a mean of 0 and with error variance. right? So these are basically some of the um, assumptions. All right, what is the problem? Here, please, can you upload? Why? What is the problem with you? AG1041. What is the problem? Maybe the problem is from your side, not from my side, right? Okay. All right. Uh, so after assuming all the assumptions, we can go for the first design. This is the first design that we are going to talk about. The first design, this is called as CRD design, complete randomized design. So complete randomized design. So this is called as CRD. Sometimes in certain books, it's called as one factor design, complete randomized design, or one factor design, right? Or CRD. Sometimes as this CRD also called as one-way ANOVA. I will explain why it is one-way ANOVA, right? We talked about ANOVA earlier. Can you remember? Where did we talk about ANOVA? Anyone? Where did we talk about ANOVA? Can somebody tell me where did we talk about ANOVA? Yeah. Yeah. Yes, regression. In regression, we talked about ANOVA. The same setup of ANOVA that we are going to use it here. Analysis of variance. What do you mean by ANOVA? Analysis of variance, nothing else, right? Yeah, people said regression. Good. So at least some could remember what we learned. ANOVA, analysis of variance. ANOVA mean analysis of variance, right? So analysis of variance, we call it as ANOVA. The same concept of ANOVA that we are going to use for the whole course hereafter. So this is a one-way ANOVA, generalizes the two sample t-test. Can you remember we said two sample t-test, right? When you talk about this two sample t-test, can you remember two sample t-test? Let's say I have T1 and T2, right? So here I have observation, here I have further observation. If I want to compare T1 versus T2, then I will go for, these are independent sample, then I will go for pooled t-test, right? Pooled t-test. Now let's say I have one more additional treatment. We can have more than two, right? Maybe 3, 4, 5, whatever. Let's say I have 3 treatment, T1, T2, T3. In pool t-test, we can compare only 2 at a time. We can compare only 2 at a time. So in this experiment, how many times we will have to do t-test if we are performing t-test? T1 versus T2, T1 versus T3. At a time, we can compare only two. T2 versus T3. So how many times we are doing? 1 time, 2 time, and 3 times. So we'll have to do 3 times of this pool t-test. So rather than doing this pool t-test for 3 times, we are performing the analysis of variance, right? So that is what I said. If you have more than 2 treatments, sorry, right? So here what we say is if you have more than 2 treatments, so if it is a 2 sample case, if it is 2 sample case, we'll simply go for t-test. But if it is more than 2 sample, right, then we go for ANOVA. If it is more than 2 treatment cases, more than 2 means it can be 3, 4, 5, but all are independent. Then here, these are the conditions when we do this CRD design. When we do CRD design, the conditions. What are the other conditions? Right? When we do CRD design, one condition is it should be more than 2 treatments or 2 independent samples. The second most important condition is the experimental units are more or less relatively homogeneous. What do you mean by homogeneous? If you take a class is not a homogeneous. Why? You have male and female. 2 different species, gender. So it is not a homogeneous. So when you do experiments for CRD design, we need to have uniform or homogeneous experimental units. Therefore, we cannot do experiments in the land. In the land, as we said, right? Let's say the place A and place B, or location A, location B on the land. So this location has a different in terms of fertility, etc., compared to location B. So these 2 locations are having different conditions. So this is heterogeneity condition. It's called as heterogeneity condition. For the heterogeneity condition, this design, CRD design, cannot be applied. So what kind of places are much more suitable for this kind of experiment? CRD laboratory. If you look at the laboratory more or less the conditions are same in everywhere, right? Everywhere laboratory conditions are more or less same. Similarly, plant house, net house, right? All the indoor experiments can be considered as homogeneous, right? Right. The other fact is the experiment will use very few replicates. So you will be using very few replicates, right? We will be using very few replicates, not very high level of replicates. And treatments are assigned to experimental unit at random. So that is another important aspect. This is true in all the experiments. This is true in all the designs. This is true in all the designs, not only here. In all the designs, treatments are assigned to experimental unit at random. All right. The last point. Each treatment is replicated the same number of times. It is called as balanced design. All right. Balanced design. For example, um, just a second. What do you mean by balanced design? What do you mean by balanced design? Let's say I'm doing an experiment. Now tell me, how many replicates are there for A, B, C, and D? How many replicates are there for each of those? For A, how many replicates? Vishmika, how many replicates for A? Yeah, A 3. What about B?
E3, sir.
3. C?
3.
Sorry. What about B? B 1, 2, 3. All right. Okay.
3.
C is
3, sir.
3. What about D?
3, sir.
D is 3. Right. Now, what do you think about the number of replicates for each treatment? Same or different?
Same.
Same. You see, A is appearing 3 times, B is appearing 3 times, C is appearing 3 times, and D is appearing 3 times. So this kind of design is called as balanced design. Right? Now what I'm going to do is I'm going to play with a little on. Now tell me what is the setup? Hmm?
In B, there's 4.
Yeah, B there's 4. What about others? B there is 4. Then what about A?
A3.
B 4. What about C?
3. D2.
D 2. Right. Now B 4, D 2. So altogether we have 12 observation. That is altogether we have 12. That is remaining same. Now you see it is unbalanced. Why? Why it is unbalanced? Here it is 3, here it is 4, here it is 3, here it is 2. Different values. So this is called as unbalanced design. So when you do experiments, don't forget this, when you do experiments, the balanced designs are always better. Balanced designs are always better. Why? For example, I'm going to give a tug of war. Anyone doesn't know what is tug of war? Team 1 is having 3 members. Team 2 is having 5 members. So 1 is here, 2 is here. Tug of war. In Tamil, it is called as Kairalathal Poti. In Sinhala, Lanu Adima. Lanu Adima. Right. So now tell me who has more chance to win in this tug of war. The team 1 is having 3 members. Team 2 is having 5 members. Who is having more chance to win? Answer me. Answer me. Now these are the
Second
simple.
team.
Second team. Yeah. Second team has more chance. Right? Why? Because it has more members. Similarly, you see here in the experiment also, when you have more and more replicate, that particular treatment has better estimate. We call it as estimate. All these experiments are done to obtain the estimate, mean and the variance. So when you do the experiment, for example, in this case, B will be estimated at high level because it is having 4 replicate, 4 observation. Similarly, D has only 2 replicate, so their estimation is very poor estimation, right? What is this estimation mean? Let's say I have 30 members in the class. I'm going to measure the average height, right? So in first occasion, the actual average height is this. The actual average height is somewhere there, right? Out of this 30 members, the actual average height is there. So in the first occasion, I will take 5 members as a sample. What do you think about the right? In the second case, I am taking 10 members as the sample. So can you guess where this 5 estimate will be and the, let's say, the 10 estimate? So this is the actual value, huh? This is the actual value. When you estimate using small sample size, the estimate is somewhere there. We don't know whether it is positive or negative side. All right? This is for 5 sample. When you have more sample, this estimated value will be much closer to the actual value. So this will be with 10 sample size. So it is coming towards, when you increase the sample size, it will come towards the actual value. So that is the speciality of this estimation, right? That is the speciality of this estimation. So when you estimate, right? When you estimate, the estimations are much more accurate when you have more and more replicate, right? So that is why we need to have more replicate, right? So here the estimation by this estimating B will be have high precision on the estimate. When you estimate the D, it will have low precision. So that is the difference, right? Right. Any questions? If you want, we can have only 5 minutes break. 5 minutes break. Okay. Okay, we will continue. Uh, Complete randomized design. These are some of the conditions for complete randomized designs, right? Uh, Balanced design. I mean, you don't need to have always balanced design. You can have unbalanced also. But only problem is if it is a balanced design, all treatments will be estimated equal because the replicates are same. If it is unbalanced, the one which is having more replicate will be estimated much higher with precision compared to the one which is having lower replicates, right? Can you all hear me? Yes? Can you all hear me?
Yes, sir.
Yeah, okay,
Yes,
right.
sir.
Okay, so this is one example where the complete randomized design could be, this is one design, right? How complete randomized design could be arranged. So this is one treatment. This color is one treatment, right? Let's say I will put it as one. The black color is a second type of treatment. The white color is third type of treatment. So it is placed randomly. Let's say this is a laboratory. This is a laboratory, right? This is a treatment 1, 2, and 3. This is a laboratory so that we can place, let's say you are doing some experiment with Petri dish, right? If you are doing some growth of some microbes using Petri dish, you can keep the Petri dish all over the laboratory or maybe any area of the laboratory. So that is this is basically called as randomization. So there is no any pattern, no pattern existing here, right? So this is good. So this is a good design. Why? Number of replicate is same, 4 for black, 4 for white, and 4 for this blue color. So randomization is okay, right? What about the others? Just a second. Huh? Right. What about the second one? This is you see this is one treatment. This is another treatment in red in color. This is 2. This is, let's say, 3. Three different treatments are there. How many replicates for one? White color? 1, 2, 3, 4, 5.
5,
What about red color?
6,
Yeah. For 1, it is 5 replicate. For 2, it is 6. What about green color?
9,
9. You see? This is called as unbalanced design. This is balance. For one, for all we have, sorry, 1, 2, 3. For all treatments, we have 3 each. Sorry, 4 each. 4 each. So this is a balanced design. This is an unbalanced design. So we'll have to decide whether we go for this kind of design or this kind of design. But the most appropriate is this. But in certain cases, we can go for that unbalanced design. Maybe we are not going to talk about much on unbalanced design here, but this is also fine, right? In we can do research on unbalanced design. This is fine, but as I said, only problem is here treatment 3 will be estimated with much more higher precision. Next, treatment 2 will be estimated with the higher precision. The lower precision will be for treatment 1. So that is the only thing. But we can have any design as we want under the complete randomized design. Right? Right. So this is another example. Now you see what is the problem here. This is a CRD design, but here there's a small problem. Can somebody identify what is the problem there? What is the problem? Anyone? You see,
Similar treatment.
yeah, go ahead, no problem. You see, there's a pattern, isn't it? Here you have yellow color, I mean, one treatment, then the next treatment, then the next treatment. Can you see? Then next treatment. So the some pattern is going on. So this is not properly randomized. This is not randomized properly. So this is not a good way to arrange the treatment. This is not the good way to arrange the treatment. Why? Because there's a pattern, right? There's a pattern. There's a pattern. So what is the problem with the pattern? You see, this is right. One treatment, second treatment, let's say third treatment, again first treatment, second treatment, third treatment, right? Again first treatment, second treatment, and third treatment, and so you see, there's a pattern. So this is not a good in terms of randomization, right? So therefore, we'll have to do the randomization in a proper way, right? There's some periodicity. So this is again a problem, isn't it? Can somebody tell me what is the problem here? Here, this area is only with one treatment, only green color. This area is only with one treatment. Problem, isn't it? So this is not randomization. So here, this design also not a good design because the randomization has been done not according to the randomizing principle. Right. Now we are coming a little more to some mathematical formulation. Right? Mathematical formulation for complete randomized design. We have three components. Right? So this you should remember without much thing. You'll have to consider this. This is observed value. Each observed value. Usually we give with the notation. I will come to that notation a little later. Yij, for example, right? How we give the notations, I will come to that. Yij, it is the observed values, right? Each observed value. For example, y11, y12. So likewise, y21 as an example. So these are different values. Each of these are different observed value. I will come to that explanation. So this observed value, right? Let's say this yi, sorry, yij. I write down, maybe it is not there. I is referring to treatment. Write down what is not there appearing. J is referring replicate. I is referring treatment. So right, I is referring treatment. J is. So Yij, I will erase this. I need some more to write down. Yij mean, I don't know whether I get it now. Just a second. Huh? Yij, right? I mean treatment. I mean treatment. J mean. It's called as observed value of I treatment. Observed value of I treatment in jth replication. So this is how we interpret Yij. Others have already interpreted there. Yij is the observed value of I treatment in jth replication. Right? For example, let's say I have treatment 1, treatment 2, treatment 3. 3 treatments are there. I will put it as replication 1, replication 2, and replication 3. Right? So this is called as, can somebody tell me? This is called as Y. So always remember the first digit, which is I, referring the treatment. The second digit, J, referring the replication. So how I can write the observed value of T1 R1? 1, 1. What about this? Y, first treatment, second replicate. First treatment, third replicate. Similarly, this one, Y, 2, 1. Y, 2, 2. Y, 2, 3. So these are indications. Y, 3, 1. Y, 3, 2. Y, 2. So this is how we indicate the observations. Can somebody has any problem identifying? Indika, if I say Y33, what do you mean by that? Indika?
Yes, sir.
Yeah. Y33 mean? First digit indicating what?
Three.
First, yeah.
Then replicate.
Yeah. First digit indicating the treatment. Second digit
one.
indicating the replicate.
Replicate.
All right. So this is how we write down the observations, each and every observations, right? So that each observations are equal to the grand mean, or sometimes called as overall mean. So, or grand, G-R-A, grand mean, grand mean plus, this is called as the treatment effect. Which treatment effect? This is the I treatment effect. So it is called as I treatment effect. Plus, this is the random error. This is called as random error. All right. I will write down EIJ. Random error of what? Random error. I will just abbreviation. Random error of I treatment in jth replicate. Hereafter, I will write treatment TRT, replicate RET. So EIJ mean random error of I treatment in jth replicate. Clear? So this is how we explain each component. This is called as model for the CRD. Write down. Model for the CRD. Model for the complete randomized design. It is the mathematical model for the complete randomized design. So each observation can be partitioned into 3 components: grand mean or the overall mean, treatment effect, and the remaining is called as random error. This random error is not unknown to you. Where did you see this random error? In your first course? Anyone? You have seen this random error before. Where did you see this random error? Anyone? Hello. Where did you see this random error? Tanushan, are you around? There are 3 Tanushan. Tanushan 1, 2, 3. Random error, where did we see? Vaishnavi?
In regression, sir.
In regression, yes. That is in regression, right. So this random error, we have put up a regression model. Can you remember? In that model, we have included this random error. Similar to that concept, because we are talking about ANOVA. So this random error, we will learn little by little. Okay, fine, good. Right, I'm going to erase. Shall I erase this? I'm going to erase this. Huh? Right. Now, this is the model. We have given the model. So this is the model, right? This is the CRD model. So if I ask, write down the CRD model, this is the model. Not only writing the model, we'll have to explain each of these components in the model. So we'll have to explain what is this, what is this, what is this, and right, what is this. We'll have to explain. Right, now, based on this model, treatment effect. This is the treatment effect. So we can write down our null and the alternative hypothesis. Our null hypothesis, any number of treatments. Simply we say alpha 1 equal to alpha 2 equal to alpha 3 and so on. Alpha t number of treatments. So where we can say, write down this I starting from 1, 2 and goes up to t number of treatments. J starting from 1, 2 and goes up to R. So normally when you have number of treatments, we indicate by T, number of replicate we indicate by R. So these are the information not available on the screen. So better write on your notes, right? So based on that, we can put up our null and the alternative hypothesis. Null hypothesis, let's say it's similar to earlier one. T1 is equal to T2. Can you remember? In our null hypothesis, what is our null hypothesis in pool t-test? Mu1 equal mu2. Can you remember? Yes? Mu1 mu equal to mu2. Right? In pool t-test. In pool t-test, that is the case. So if you have 3 treatment, so our null hypothesis goes further. Mu1 is equal mu2 is equal mu3, etc., etc. So the same thing that has been given here. So here we have, I will clear all again. Alpha 1, that is the first treatment effect. It's similar to mu1, the same as mu2, same as mu3, and so on, so on, so on. So what do you mean by all these mu1 is equal mu2 is equal mu3? If you accept this, what do you mean by, is there any, this is treatment 1, this is treatment 2. This is treatment 3. Is there a difference between these 3 treatments? If mu1 is equal mu2, mu2, mu3. Anyone? Vidusha? No treatment effect. We can write it as no treatment effect because this is same as this is same as that, so all equal, isn't it? So there is no treatment effect. All treatments are behaving similar. All treatments are behaving similar. So no treatment effect. Right, now let's say one, we cannot write suppose let's say this is not equal. I have only 3 treatments. This is not, if you compare 1 and 2, so this is my outcome. Let's say this is my outcome. If I compare alpha 1 and 2, is there a difference? Yes or no? Look at, no difference. I'll put it as no difference. What about alpha 1 and alpha 3? By looking at this, anyone? Yeah, not equal. The mean of alpha 1 is not equal to mean of alpha 3. So different, it is different. What about alpha 2 and alpha 3? Not equal. So that is also different, you see. So this we can write as this, can we? For example, therefore we don't know exactly how many not equals coming in between. So we write it as at least one of the alpha different from 0. So all, this is not mean, right? This is treatment effect. We call it as treatment effect, not the treatment mean. This is a treatment effect. These treatment effects are equal to 0. That is our null hypothesis. The alternative hypothesis, at least one of the alpha is not equal to 0. Or we can say at least one of the alpha is differ from 0. Right? Clear? Right. Okay. So we will continue. Any questions? Advantage of complete randomized design. What are the advantage of complete randomized design? It has more flexibility. Any number of treatments and any number of replications are possible. As I said, in earlier case, we have shown that the replication need not to be equal. The replication need not to be equal. We can have a different level of replication. Still, we can do the analysis. But only difficulties or the different is that the estimations will be different. Estimations will be different. Precision of the estimation will differ, right? But we can have a different number of replications. We don't have the same number of replications per treatment. But if you have equal number of replications, it is more efficient, as I said earlier. We need simple statistical analysis. Very simple. Even if you have unequal replications, we can do statistical analysis, not a problem. Once you come to Pinocchi, we may do some practicals. I will show you some practicals, how to do it using computers, different softwares. The other thing is missing flux do not complicate the analysis. We are not going to talk about missing flux in this particular course. There may be a chance of missing flux. What do you mean by missing flux? Right? Initially, I take let's say I take 3 for A, treatment A, 3 pots. Let's say pots, 3 pots. For B, I take again 3 pots. For C, I take 3 pots. Suppose, let's say, due to some reason, the plant in pot C is died. The plant in pot C is died. Initially, I took all with same number of replicate. Now I have only 3 replicate. I mean 3 replicate for A, 3 replicate for B, and for C we have only 2 replicate. So even if there are missing flux, these can be considered as flood. Each of these can be considered as flood. So even if there's one is missing, still we can complete the analysis in the CR. So that is the specialty of CR. Maximum error degrees of freedom we obtain. We will talk about what is this error degrees of freedom. Right. Next one is design construction. No restrictions on the assignment of treatments to the flux. Each treatment is equally likely to be assigned to any flux. Should use some sort of mechanical procedure to prevent personal bias. So that is should be there. So you should avoid the personal bias. Assignment of random numbers may be, you can draw a lottery. A computer can assign using a random table. You can assign it, right? So what if, for example, let's say here what do you mean by assigning numbers? Let's say I have 3 plots, 3 pots. I have 3 treatment. What are treatment? A, B, C. So what I can do is I can number the plot. This is 1, 2, 3, 4, right? 5, 6, 7, 8. Sorry. Right. So here, right. So this is plot number 9. So this is 5, 6, 7, 8, and right. Now, how to allocate the treatments? How to allocate the treatments? Very simple. So A can be 3 times, B can be 3 times, C can be 3 times. So take 9 pieces of paper, 9 pieces of paper, right? Take 9 pieces of paper, write A, 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 B, 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 C, C, and C, right? These are different chips. Put it into the box. Shake it well. Take one by one. When I took the first one is I got C. So I'm going to allocate plot number 1 as C. Second time I got B. Third time I got C again. Fourth time I got A. Fifth time I got B, let's say. Then I got A, right? Then I got, let's say, C as an example. Then I got A. Then the last one is, you see, the last piece that I got is B. So you see 3 times C is coming, 3 times B is coming, 3 times A is coming. So this is a typical randomization. I did randomization. This is called as typical randomization. You'll have to do it randomization in such a way to avoid the biasness, right? So write down the pieces of treatment into the box, take one by one, assign those treatments to the numbered experimental units. So that is simple way of doing randomization. Right. Some are the limitations of the CRT. Right. Some of the limitations of CRT. In many situations, the researchers do not have a sufficient homogeneous experimental material. So that is one of the biggest problems. Right. Homogeneous experimental material, finding a homogeneous experimental material is a real challenge, right? Maybe in one group, maybe location, batch, etc., to effectively use the complete randomized design, or the study objectives requires examining treatments over a broad range of experimental units in order that the results can be extended to more situations. So that is another aspect. The study objective require examining treatments over a broad range of experimental units, right? Beneath the study objective. So that may be another reason why CRD is not proper idea. The next one is the experimental material must be grouped for administrative or implementation purposes. That is to say, implementation constraints. Right. Let's look at very briefly. This is the one-way ANOVA. Right. This is the one-way ANOVA. ANOVA, I don't want to declare once again. You have different components: source of variance, degrees of freedom, sums of square. SS means sums of square, mean square, and the FI. This is how we divide the ANOVA table. Source of variance, degrees of freedom, sums of square, mean square, and the FI. So here, what are the major components come? Treatments is one of the components. Can you remember in regression? Regression came as one of the source of variance. So here it is treatment. Treatment is one of the major components. Then you have the total. So total minus treatment. Total minus treatment will give the error component, right? So total minus treatment will give the error component, right? So what is the degrees of freedom for treatment? Total number of treatments, can you remember? I said earlier, if it is I, starting from 1, first treatment, second treatment, and goes up to T number of treatments. Similarly, replicate starting from 1 to goes up to R. So treatment degrees of freedom is total number of treatments minus 1. So it is T minus 1. Right? T minus 1. Treatment degrees of freedom is T minus 1. Then the next one is total degrees of freedom. T into R. That is total. T into R. Number of treatments multiplied by replicates minus 1. TR minus 1. Then if you deduct the treatment degrees of freedom, T minus 1 from that, you can show that TR minus 1 minus T plus 1. So this one will cancel off. So we can say T into R minus 1. So that is the, all right. Then we have sums of squares. Sums of square of treatment. Total sums of square. So sums of square total minus sums of square treatment will give sums of square error. So we have the sums of square. Oh, I mean error component always total minus the rest. That we have seen already in regression also. Right? All right. Right. Now mean square. Mean square is the sums of square divided by degrees of freedom. So sums of square total divided by degrees of freedom of treatment, which is giving the mean square of treatment. Similarly, sums of square error divided by the degrees of freedom of error, which is giving the mean, error mean square. Right? Ultimately, we test our treatment against with the error term. We test the treatment with the error term. So mean square treatment divided by mean square error will decide the F value. Then based on the F value, we go for whether we reject or whether we accept our null hypothesis. Right? Right. I think next time I would be able to explain the table of this table. We will come to that later. Right? That is with more elaboration. Any questions? Any questions that you would like to ask from me? You can send me through chat, no problem.